All right, what is going on, everybody? We're going to go over some of the impulse momentum stuff. And to get us started, there's just a couple things we want to know. Remember, momentum, P for momentum, is mass times velocity. So that's if I want to find a single momentum, right? Or a momentum that's at one point in time. And if I want to know something's change in momentum, then what we can do is say the change in momentum is equal to mass times, and it's not the mass that's going to change normally. Normally it's going to be the velocity. So right here we have the change in velocity, right? So change in velocity, this right here is what we call, or this whole thing, that term right there is what we call the change in momentum. Okay, so right there, change momentum is mass times whatever something's change in velocity is. There's another type of thing that we have called impulse. And impulse, I like to just write the word impulse because, to be honest, there's a bunch of different variables people use. Sometimes you'll see this as a capital J. Sometimes you'll see it as a capital I, right? All of these things, it's kind of confusing, so I like to just say impulse. And impulse is equal to the force that is acting on something, and it's being applied over some time interval. So a force times a time, and this is what we call impulse right there, okay? So there's this thing called the impulse momentum theorem, and let's go over here. We have the, let's do it in blue, impulse momentum theorem. And right there, that basically links these two things together, and we say that the force acting on something over a amount of time is equal to its change in momentum. So if you think about this, it makes sense. If I apply a force to something, it's going to make that thing change how fast it's going. Okay, so that's really all that's saying. I apply a force over a time, and it makes a mass either speed up or slow down. That's it. Okay, so that's the impulse momentum theorem, and it's how a lot of this stuff is always going to be linked together. Okay, so using that for problems that are going to arise in this skill set, we have things like this. A tennis player hits a ball and gives it a change in momentum of 6.3. All right, and here we have a problem. A tennis player hits a ball and gives it a change in momentum. So change in momentum right there, that's an important phrase, right? Change in momentum of 6.3 kilogram meters per second. So I'm going to write that down, change in momentum. Remember, we always write it like that. That's our term that means change in momentum. And that's 6.3 kilogram meters per second. Sadly, there's no better unit for that. That's just what it is. Over a course of 10 milliseconds. So that is our time interval. 10 milliseconds. And we always want to use things as seconds, right? So 10 milliseconds, milli is 1,000, so we would divide that by 1,000 to turn into just seconds. Okay, and the question is asking, what is the magnitude of the force being exerted on the ball? So I got momentums, times, forces. I'm thinking momentum impulse theorem. So I'm going to start with my momentum impulse theorem. Impulse is equal to change in momentum. And I'm being asked to solve for net force. So I'm going to rearrange this and just have it equal to force. There we go. And now we have everything. Now we can plug and chug, right? We know the change in momentum is 6.3 kilogram meters per second. We know the time is 0.01 seconds. And when we do all of this, 6.3 divided by 0.01, we end up with a force of 630 and kilogram meters per second divided by seconds would give us kilogram meters per second over meters per second squared, right? These two combine to make squared. Well, that's a mass times an acceleration, so the units work out because this would be 630 newtons. Cool? All right, let's take a look at the next one. Frisbee hits a window and stops in 10 seconds, or 0.10 seconds. So that's our time. Just kind of, I like to write things down as we get to it. The net force on the Frisbee is 75 newtons. So there's a, what's the magnitude of the change in momentum? Okay, so start with our impulse momentum theorem. We're being asked to solve for change in momentum, so that's this whole side over here. And I have force and time, so really it ends up just being plugging in what we have. Right, 75 newtons times 0.01 seconds, or that's actually 0.1 seconds. And that is going to equal 7.5 and a newton times a second, which is kind of weird. So let's do a little scratch work down here. A newton, 1 newton times second. Well, that's the same thing. Remember, a newton is a mass times an acceleration, right? So newtons can be written as a kilogram, mass times acceleration, and then times the seconds. Well, if you see what happens there, one of those seconds cancels, and we'd be left with a kilogram times meter per second, or a mass times a velocity, right? So that's our units for momentum. So we're good to go. Let's see. A bowler tosses a 6 kilogram ball from rest to a final velocity of 10 meters per second. So let's just, again, let's keep track of what we got so far. We got a 6 kilogram bowling ball, so that's our mass, or a mass at least. From rest to a final velocity of 10 meters per second. So I have two velocities there. I have an initial velocity of 0 because it's at rest, and then a final velocity of 10. Okay. Rolls down the bowling alley. What is the magnitude of the change in momentum? So there's no, if you think, okay, I need to, we're being asked to find the change in momentum, right? Well, we could start with, maybe you like that kind of process and you go, all right, I'm going to start with impulse momentum. But the problem is we don't know any forces or times, right? So take a look at what this is. Mass times how much the velocity changes. I have the mass and I have the two velocities. So we're actually going to expand on this piece right here. So what that's going to look like is mass. Remember, change in velocity is, change in anything is always the final one minus the initial. And so we can just keep on plugging that in. We got mass is 6 kilograms, right? The final velocity was 10 meters per second, and the initial velocity was 0. So when we plug all that in, we got 6 times 10 to give us 60. And this is a kilogram times a meter per second, which is good because that's our units for momentum. Cool, that one's easy peasy. Nice and quick. A pitcher throws a 0.15 kilogram baseball, and it's going 35 meters per second to the east. And then other thing is, it says in the end, we're going to say east is in the positive direction. So we got a mass of 0.15 kilograms, and here's a velocity. The batter hits the baseball and sends it in the opposite direction, going 50 meters per second to the west. So we have an initial velocity of this one, 35 meters per second. And east right there is in the positive direction because of that, right? So we're going to say positive 35 meters per second, which means that this, if it's going in the opposite direction, west, the final velocity will be negative 50 meters per second. And we're being asked, what is the change in momentum? All right? So very similar to the last problem, just now we have these, the velocity changing is a little bit different. So we could start with impulse momentum. And then you could realize, oh, I don't have any of forces or times, but I do know how much the velocity changes. So we just keep on going, right? That's a final velocity minus the initial velocity. And now we can plug in what we have. We have mass is 0.15 kilograms. The final velocity down here is negative 50. So negative 50 minus the initial velocity, which was positive 35. All right? And now we just, this whole thing turns into negative 85. And that would be negative meter per second. Now, one other thing, this says magnitude, right? Magnitude means we don't care about the direction. So this right here can go away. So our final answer would just be 12.75 kilogram meters per second. Uno más. Tennis player hits tennis ball, changing its momentum by 25 kilogram meters per second. So change in momentum right there is 25 kilogram meters per second. All right. The net force is 5,000 newtons, so 5,000 newtons. How long? So how long is asking for some time interval. So that looks like what we're going to be solving for. Okay, so we start with the impulse momentum theorem. Mass times change in velocity. And then really just solve for time now. All right, rearrange this. Have it solved for time. Good morning. Now we can plug everything in. It's all right. And that would give us a final answer of 0.005 seconds. Boom. All right. I will catch you guys later.